Welcome to the Sleepy Cosmos channel, a place where science and serenity meet. Here we explore the quiet wonders of the universe, from dark matter to string theory, all told in a calm, soothing rhythm designed to help you relax, drift, and dream among the stars. Each video is a guided journey through the cosmos, slow, meditative, and filled with real science wrapped in gentle storytelling. So if you love space, curiosity, and the peaceful side of knowledge, you're in the right place. Make sure to subscribe for more new sleep narrations every week. And if you'd like to reach out for collaborations or business inquiries, you can contact us at the sleepycosmoschannel@gmail.com. Now, settle in, take a deep breath, and let's drift into the universe together. Tonight, you are not here to solve anything. You are not here to memorize equations or wrestle with the strange behavior of gravity or follow every detail of how space-time bends. Tonight is for rest and for the quiet kind of curiosity that asks nothing of you. Just let the ideas drift toward you, softly, the way light drifts across the surface of a calm lake. And as you listen, you might notice that black holes, the universe's most mysterious objects, are far gentler and far more predictable than the dramatic stories often make them sound. A black hole is not a violent monster waiting to swallow the sky. It is a stable, mathematically elegant, perfectly behaved solution to the laws of physics, and understanding them, even a little, does not require effort. It only requires drifting. Drifting into the thought that gravity, the same gentle pull that keeps your body resting on your bed, can become strong enough and steady enough to fold space-time into a quiet well, a well so deep and so perfectly shaped that not even light can climb back out. As you settle deeper into your breathing, let that image soften, turning from something dramatic into something serene. A black hole is simply gravity at its most complete, its most concentrated, its most still. And tonight, all you have to do is let the calmness of that idea move through you. No pressure to understand everything. No pressure to stay awake for every explanation. If you drift away, that is perfectly fine, because the science will keep flowing gently. Whether you are listening with full focus or floating on the edge of sleep, black holes are simple objects, surprisingly simple, and their simplicity has a way of quieting the mind. Mass, spin, charge, these are the only qualities a black hole keeps. Everything else is smoothed away, all the messy details of the star that collapsed. The turbulence, the heat, the complicated mixtures of elements, all gone. What remains is pure geometry, a curved region of space-time defined by only a few numbers. It is as if nature takes everything chaotic, everything noisy, everything unpredictable, and presses it into a form so simple and so stable that it becomes one of the most peaceful objects in the universe. And as you breathe, you can imagine that simplicity, like a soft gravitational lullaby. The deeper the curvature, the more perfect the shape becomes. Smooth, quiet, inevitable. Black holes are not places where physics breaks. They are places where physics becomes incredibly clean, where the equations sharpen into something almost serene. And tonight, these calm truths will unfold slowly, like pages turning in a book you do not need to finish. Just let your mind wander across distances so large they become soothing, across timescales so long they feel like gentle tides. Black holes are part of the universe's deep structure, not chaotic intruders, but quiet anchors, shaping the stars and galaxies around them with silent precision. And as you settle deeper into rest, you may find that listening about them has the opposite effect of fear. It brings stillness, order, clarity. Because even though black holes are powerful, their behavior is predictable, mathematically exact, and almost meditative in how they shape space-time. Tonight, you will drift into that calm. You will explore how a black hole curves space-time, how time slows near its horizon, how matter spirals inward with quiet inevitability. You will hear how falling in can be strangely uneventful, and you will drift through the gentle mystery of why some information slips forever beyond our reach. Not with urgency, not with intensity, but with the soft rhythm of a scientific lullaby. And as your mind relaxes, you may begin to feel the same stillness that defines a black hole itself, perfectly calm at the boundary, perfectly smooth at the horizon, a kind of cosmic quiet so deep that it almost invites sleep. So let your thoughts soften, let your breathing slow, Let the universe expand around you, not as something overwhelming, but as something vast and patient, something that has been here long before you and will remain long after, something that expects nothing from you tonight except rest. And in that rest, you might feel a small sense of wonder that the most extreme objects in the universe can also be the most peaceful to think about. Because the truth is simple. A black hole is not chaos. A black hole is order. A black hole is not noise. A black hole is silence. A black hole is the universe falling inward toward its own simplest form. And as you drift, you can imagine that inward motion as something gentle, like a slow, steady, gravitational exhale, folding space-time, not violent, but inevitably, smoothly, quietly, into a point of perfect stillness, into a center that needs no more explanation, into a place where everything becomes calm, where everything becomes simple, where everything becomes quiet. Let that quiet fill you and carry you forward into the next moments of this journey. When you picture a black hole, you might imagine something sharp, dangerous, chaotic, but the reality is almost the opposite. A black hole is the most gently shaped object gravity can create, a smooth, continuous curve in the fabric of space-time, a quiet bowl carved not into matter, but into the geometry that matter moves through. If you could somehow float near one without falling in, you would not see jagged edges or turbulent surfaces. You would sense a kind of perfect symmetry, a calmness in the way gravity pulls from every direction with the same steady strength. This is one of the most relaxing truths in physics. Space-time curve does not bend suddenly. It does not twist violently. It deepens gradually, like a slope becoming gently steeper the farther inward you drift. And that curve, that slow, steady, gravitational descent, is what defines the geometry of a black hole. Not chaos, but precision. Not noise, but silence. A black hole is simply the smoothest place where gravity has reached its fullest expression. The boundary of this shape is the event horizon, a surface that is not actually a surface, but a location in space-time where escape simply becomes impossible. What makes the horizon soothing to imagine is that nothing physical changes there. No wall, no barrier, no glowing ring of fire, just a point where the inward pull quietly surpasses every outward possibility. From the outside, the horizon looks frozen, perfectly still, like a dark, motionless sphere suspended in the fabric of reality. Its stillness is not a trick. It is a direct expression of the math, a point where light itself finds no path forward. And yet, to an object falling in the horizon feels completely ordinary. This is one of the most calming ideas in all of relativity. Locally, the edge of a black hole is perfectly smooth. You would not feel a sudden drop or a violent shift. Your motion would remain uniform and gentle, guided only by the natural path, the geodesic, that space-time provides. This is why we say that black holes are simpler than stars. A star has layers, turbulence, magnetic storms, nuclear reactions, fusion cycles, convection zones. A black hole has none of these. It has only a geometry, a curvature so clean that the entire object can be described by a radius, the Schwarzschild radius, which marks the boundary beyond which escape becomes impossible. The simplicity of that radius is part of the calm. It depends only on mass, nothing else. Double the mass, double the radius, triple the mass, triple the radius. Gravity shapes the horizon with perfect proportion, perfect balance. A sphere defined only by how much mass has been gathered into one place. And yet, even as the horizon grows larger with increasing mass, its surface remains completely smooth, no ripples unless something disturbs it. And when it is disturbed, a black hole releases those ripples as gravitational waves, gentle vibrations of space-time. These waves fade, calm down, and the horizon settles back into perfect stillness. This settling, this natural return to equilibrium, is another reason black holes feel peaceful when described scientifically. Their geometry is stable, self-correcting, always returning to a quiet state after any disturbance. Imagine water in a perfectly round bowl. If a drop falls and the ripples spread outward, fade, and the water returns to silence. A black hole behaves the same way, but in space-time itself. This stability is not just poetic, it is mathematical. In general relativity, the equations governing a black hole produce solutions that are smooth, predictable, and elegantly curved, which means that the deeper you imagine going, the more gently the curvature changes. The steepness grows, but it grows smoothly, never suddenly. Even near the horizon, the curvature remains soft, the gradient gradual. This is why falling inward feels uneventful. The change is continuous, not abrupt. Your path bends because the geometry bends, but the bending is natural, like following the shape of a valley rather than tumbling off a cliff. And as you picture that descent, not as a fall, but as a drift through curved space-time, you might notice something else. Black holes are some of the few places where the universe becomes simpler the closer you get. Far from the horizon, gravity is weaker, space-time is flatter, the geometry is less focused. Near the horizon, the curvature gathers, organizes, tightens into a single clean shape. Nothing chaotic, nothing random, just the gentle deepening of a gravitational well. This is why black holes are among the easiest objects in the universe to describe mathematically. Their geometry contains no unnecessary details, no extra features, only pure curvature. And that purity makes them deeply soothing to think about. You can imagine space-time as a flexible sheet. Place a small mass on it, and the sheet bends slightly. Place a larger mass, and the sheet bends more. But place enough mass in a single point, and the sheet deepens into a perfect well, a smooth funnel with no edges, no breaks, no sharp turns. That is the essence of a black hole, gravity curling inward in the most elegant way possible. And when you imagine that funnel, try to picture its surface, not jagged, not trembling, but smooth, polished, quiet, a sphere of perfect symmetry. Every point on that sphere experiences the same curvature, the same pull, the same silence. In this sense, a black hole is almost meditative, a place where the universe lets go of complexity and settles into the simplest form gravity can make. And as you rest, you may find that simplicity calming, because part of the mind's restlessness comes from complexity, from too many details, too many directions. Black holes remove details, remove directions, remove everything but the clean curved shape of spacetime itself. They are the universe reduced to geometry, a geometry so quiet and so stable that it becomes a kind of cosmic stillness, a stillness you can drift into, slowly, softly, without needing to hold on to any one thought, just letting the shape carry you inward, the way spacetime itself carries everything toward the calm, smooth, silent horizon. The deeper you let your mind drift into the geometry of a black hole, the clearer it becomes that everything about its structure is defined by calm, mathematical inevitability. Nothing inside this geometry is rushed. Nothing is abrupt. Even the strongest gravitational pull in the universe unfolds gradually, with a steady gradient that guides everything inward as if following the curve of a quiet spiral. This gentle gradient, the way spacetime bends more and more as you move closer to the center, is the essence of how gravity shapes the region around a black hole. Imagine standing far away, so far that gravity feels almost non-existent, and then taking slow steps forward. With each step, the curvature deepens slightly, just a little more than before. There is no cliff, no sharp transition, only a continuous smoothing as spacetime folds inward. This smoothness is one of the most soothing facts in physics, because it means that even though the gravitational pull becomes overwhelming near the horizon, the transition to that state happens gradually. The curvature increases with perfect continuity, like a slope that grows steeper but never jagged. And at the heart of this shape is the event horizon, not a physical barrier, but a geometric threshold. It is simply the point where every possible path forward bends inward, where the geometry offers no outward direction. You can imagine it as a perfectly still spherical shell surrounding the center. No matter approaches the horizon in a chaotic way, it approaches smoothly, its trajectory bending as if guided by invisible rails. The event horizon is quiet. It neither emits nor reflects light, but it holds its shape with absolute steadiness. To an outside observer, anything falling toward the horizon appears to slow down, stretch, dim, and freeze. But this is not the object itself changing. It is the geometry of spacetime altering the way light travels outward. From the falling object's own perspective, everything remains perfectly normal. Its clock ticks at its usual pace, its motion feels smooth, and the horizon does not feel special. This is one of the most elegant aspects of black hole geometry. What looks dramatic from far away feels calm and uneventful nearby. The mathematics behind this idea is deeply precise, yet relaxing to imagine. A black hole does not pull in the way gravity is often described. It simply shapes spacetime so that the straightest possible path leads inward. A falling object is not being yanked, it is gliding along a geodesic, the natural curve that spacetime tells it to follow. And because spacetime itself is smooth, the object experiences smoothness as well. Even near the horizon where gravity is strongest, the curvature remains continuous. There is no spike, no sudden change, no violent snapping of the trajectory, just the deepening of the slope, just the quiet steepening of an already smooth curve. The Schwarzschild radius, the distance from the center to the event horizon, marks the boundary of this gravitational well. This radius depends only on mass. A black hole with more mass has a larger horizon, a wider bowl, a gentler curvature near the edge. This is another calming truth. The larger the black hole, the gentler the gradient at the horizon. A supermassive black hole has such a slowly changing curvature near its event horizon that you could drift across the boundary without noticing. No sudden stretching, no ripping, no turbulence, just a smooth continuation of the path you were already on. The simplicity of the Schwarzschild radius is part of the reason black holes feel so serene when described scientifically. There is no complicated structure to memorize, no chaotic swirl of forces, only a single number that defines the entire shape. A star of similar size would contain layers, fusion zones, convection currents, magnetic storms. A black hole contains none of these. It is pure geometry. The interior region is defined by the curvature of spacetime and nothing else. And when a black hole rotates, the geometry stretches and twists slightly, but even that twist is smooth and continuous. Rotation does not create turbulence. It creates a gentle frame-dragging effect, a slow, steady turning of spacetime, like stirring honey instead of water, thick, smooth, gradual. The most extreme forces in the universe express themselves with the quietest math. Even when two black holes merge, an event that can release more energy in a few seconds than all the stars in the observable universe, the geometry behaves with elegance. The horizons ripple, but not chaotically. They vibrate in specific modes, called quasi-normal modes. These vibrations are like the ringing of a bell, clear, mathematical, predictable. Each ring carries information about the mass and spin of the final black hole. And then, after a short time, the vibrations fade, and the surface returns to perfect stillness. This ability to settle, to calm itself, to relax back into equilibrium is one of the most beautiful aspects of black hole geometry. It mirrors the way a mind settles after a disturbance, the way thoughts ripple for a moment and then fade into quiet. Just as a black hole absorbs disturbances and returns to balance, you can allow your thoughts to drift through and settle naturally, smoothly, slowly, inevitably. Another soothing truth lies in the symmetry of a black hole. Every direction around it shares the same curvature, the same gravitational pull, the same mathematical structure. It is a perfect sphere, not because of pressure or heat, but because gravity shapes spacetime with complete equality. This symmetry creates a kind of cosmic peace, a shape that is the same no matter how you turn it, no matter how you approach it. Symmetry is calming to the mind, and black holes are among the most symmetric objects that nature can produce. The closer you imagine moving toward the horizon, the more uniform the geometry becomes. Everything points inward, not forcefully, but with the simple inevitability of a valley leading toward its center. The mind can rest in that inevitability, in the knowledge that nothing chaotic waits beneath the surface. Only a deepening curve, a gravitational shape formed entirely from continuity. Black holes are simpler than stars, simpler than planets, simpler than atoms. Their entire identity can be summarized with only a few parameters: mass, spin, and, if present, charge. Nothing else remains. All the details of the matter that formed them are erased, smoothed, absorbed by the geometry. What survives is the shape itself, a perfect solution to Einstein's equations, a solution so stable that it can last for trillions upon trillions of years. And in that vastness of time, in that immense stillness, the black hole keeps its shape, quiet, unchanging, resting at the center of its own space-time. As you imagine that shape, you might feel your mind settling into a similar stillness. You do not need to hold on to every detail. You do not need to follow every idea to completion. Just drift slowly, following the curve wherever it leads. Because the geometry of a black hole is not a place of chaos, it is a place of order, a place where space-time gathers itself into the most elegant form it can take. When you think about the universe, you might imagine complexity everywhere. Stars boiling with fusion, planets with layered atmospheres, galaxies full of turbulent dust and magnetic storms. But black holes do not belong to this world of complexity. They are the opposite. They are simplicity in its purest physical form. Once a black hole has settled, once all the temporary vibrations and brief distortions have faded into the darkness, it keeps only three qualities: mass, spin, and charge. Everything else, every piece of information about the matter that formed it, is washed away. This is the essence of the no-hair theorem, a poetic name for a very precise mathematical idea. Black holes have no hair, no extra details, no traceable features that reveal their past, just the clean parameters that define the geometry of spacetime around them. This simplicity is surprising, and also deeply calming, because it means that once a black hole forms, its behavior becomes perfectly predictable. Two black holes with the same mass, same spin, same charge are identical, not similar, not comparable, identical, down to the shape of their horizons, the frequencies of their gravitational waves, and the structure of their spacetime. This is unlike almost anything else in the cosmos. Two stars with the same mass can behave wildly differently. Their temperature, their age, their rotation, their magnetic fields, their chemical composition. All of these create variations. Stars remember their histories. Black holes do not. Once matter crosses the horizon, once it becomes part of the black hole, its details vanish from the outside world. What remains is a smooth, mathematical form. Imagine taking something incredibly complex, a collapsing star, a cloud of plasma, a storm of particles, and compressing all that complexity into a single number, mass. That is what nature does. And if the black hole spins, it keeps one more number, angular momentum. Spin gives spacetime a gentle twist, a slow, steady rotation, like a quiet vortex that never becomes chaotic. And if the black hole carries an electric charge, rare in astrophysical environments, that becomes the third number, mass, spin, charge, then the story ends. No other properties remain. This simplicity is beautiful in a mathematical sense, but it also creates a psychological stillness. Because it means that a black hole is the universe stripped of all complications. Every disturbance that touches the horizon is absorbed, smoothed, and erased. You can imagine these disturbances as ripples on a dark pool. Drop something into the water, and ripples spread outward. Drop something into a black hole, and ripples move inward. Those ripples are gravitational. They vibrate across the horizon with specific frequencies. Determined only by the black hole's mass and spin, these vibrations are the ring-down phase. The black hole rings like a bell, but its ringing is short, its tones fade quickly, and the horizon returns to perfect stillness. This is one of the quietest processes in all of astrophysics. A black hole is disturbed, it shivers, it hums, and then it relaxes, settling back into equilibrium. Always the same equilibrium, always the same shape. There is something soothing about an object that always returns to stillness. Even when two black holes collide, one of the most energetic events in existence, the end result is a single black hole that quickly calms itself. The violent merging of two enormous gravitational wells is followed by a few seconds of fading vibrations. And then, silence. A new equilibrium, a new curvature, defined by mass, spin, charge, nothing more. This ability to erase complexity is one of the reasons physicists find black holes so elegant. You do not need to know what fell in. You do not need to know the details of its structure. You do not need to track the countless interactions that happened before the collapse. All you need are those three numbers. The rest is absorbed into the geometry. And in a sense, this mirrors something true about the way the mind relaxes. When you are overwhelmed, when thoughts multiply, when details press inward, there is a kind of relief in letting the noise dissolve. In letting only the essential things remain, a black hole is the universe doing exactly that, letting go of noise, of detail, of complications, until only the simplest description survives. This simplicity also means that black holes are incredibly stable. They do not flicker with storms, or collapse into new states, or shift unpredictably. They sit at the foundations of physics like quiet anchors, steady, unchanging, and ruled by clean equations. Even their spin is stable. A rotating black hole creates a gently twisting region outside its horizon, called the ergosphere. Inside that region, spacetime itself is dragged around, but even this dragging is smooth, continuous, structured. There are no whirlpools, no turbulence, no spirals of chaos, just a steady rotation encoded in the geometry. So predictable that if you know the spin, you can calculate exactly how much energy the rotation contains, and how that energy might someday be extracted through perfectly lawful physics. This predictability is part of the calm. Everything a black hole does follows a precise pattern. Matter spirals in along paths determined by geometry, light bends along curves that can be calculated. Time itself slows according to fixed rules. Nothing is left unexplained. Nothing is random. Even the horizon, the boundary that defines the black hole, has a temperature, a surface gravity, and a set of thermodynamic laws that mirror the laws of heat and energy in ordinary systems. These laws are surprisingly peaceful. They describe how black holes exchange energy, how they settle, how they maintain equilibrium. A black hole does not fight against its environment. It simply accepts matter, absorbs energy, and returns to calm. Ripples fade, distortions smooth out, and the geometry finds its balance. Mass changes, spin changes, charge changes. But once those numbers settle, the entire object settles with them. Everything snaps back into predictability. Black holes are the most extreme objects the universe can make, yet they are the easiest to describe. One radius, one temperature, one surface gravity, one set of simple rules. The elegance of that simplicity is almost meditative, and as you breathe, you may sense the comfort in knowing that something so powerful obeys such quiet laws. In the next moments, this calm simplicity will continue to unfold as we drift deeper into the physics of these perfectly behaved objects. The deeper you rest into the idea of a black hole's simplicity, the more peaceful that simplicity becomes. Because when nature removes complexity, when it erases all the details that once belonged to the collapsing star, what remains is something astonishingly orderly. Even the smallest disturbance is handled with elegance. Imagine a black hole quietly drifting in space, perfectly symmetric, perfectly smooth, its space-time curved into a stable gravitational well. Now imagine something small falling toward it. A fragment of rock, a cloud of gas, even a stray photon. At first glance you might picture chaos, but in reality the black hole responds in the most predictable way imaginable. The object approaches the horizon, following a geodesic, the straightest possible path through curved space-time. Its motion is not random, not turbulent, not chaotic. It is a direct outcome of geometry. And as the object nears the horizon, the black hole absorbs its mass, its momentum, its energy. The horizon expands just a little, gaining exactly the amount dictated by the laws of general relativity. Even this expansion is smooth. Not a jolt, not a sudden stretching, just a gentle widening of the boundary. The black hole does not react the way ordinary matter reacts. It simply incorporates the new energy into its structure, and then settles. Every disturbance has a settling process. A brief ripple, a short-lived vibration traveling across the horizon. These vibrations are gravitational waves, and they follow strict patterns. The black hole rings with specific frequencies, just like a musical instrument. Deep, low, pure tones that fade with time. Each tone is determined entirely by the black hole's mass and spin. Nothing else matters. Not the shape of the object that fell in, not the angle of impact, not the material composition, only the fundamental parameters. This is one of the most calming truths about black holes. They forget everything that is not essential. The details vanish, but the rules remain. After the brief ringing ends, the horizon settles back into stillness, returning once again to perfect equilibrium. This return to equilibrium is not just a physical process, it is a mathematical promise. General relativity predicts that every black hole will seek the simplest possible state, a state defined by only three numbers: mass, spin, charge. All other information is smoothed out as if the horizon were made of silence. There is something deeply soothing about a system that always settles, always returns to calm, no matter how it is disturbed. Even when two black holes merge, colliding at a significant fraction of the speed of light, the aftermath is not chaos. It is clarity. The final black hole emerges with a new mass, a new spin, and if charge is present, a new charge. These numbers fully determine its shape. The rest is radiated away as gravitational waves, ripples in space-time carrying excess energy outward. These waves fade across the universe, leaving behind a black hole in a perfect state of rest. This entire process is mathematical poetry, a cosmic disturbance followed by a cosmic sigh, a settling, a return to the most peaceful configuration nature allows. And because black holes are defined so simply, we can predict their behavior with extraordinary precision. Know the mass, and you know the radius, the temperature, the gravitational pull, the curvature of space-time. Know the spin, and you know the shape of the ergosphere, the twisting of space-time, the energy that can be extracted. Know the charge, and you know how the electromagnetic field interacts with particles nearby. Everything else is irrelevant. This level of predictability is unlike almost anything else in the cosmos. Think of a galaxy, filled with stars and gas and dust, each part influencing the others in subtle ways. Think of a planet, with layers of rock and oceans and storms. Think of a star, with convection currents, fusion cycles, magnetic loops, chaotic, beautiful, but complex. Black holes strip all of that complexity away. In their presence, the universe becomes simple. The equations become clean, the geometry becomes elegant, the behavior becomes steady. This simplicity also gives black holes a remarkable stability. A black hole cannot be torn apart, it cannot crumble, it cannot explode the way stars do. Its structure is held together by the fabric of space-time itself. Gravity shapes it, gravity sustains it, gravity defines it. The same force that keeps you resting on your bed right now is the force that supports this perfectly predictable object. Scaled up, deepened, concentrated, but still governed by the same universal laws. And if you imagine the surface of a black hole, the event horizon, you can think of it as the most perfect absorber in existence. Nothing bounces off it, nothing reflects, nothing escapes. This perfect absorption is part of what makes black holes so simple to describe. All incoming information is lost to the outside world. Only the increase in mass remains. This behavior is captured in the laws of black hole thermodynamics, beautifully simple equations that tie together surface gravity, horizon area, and energy, and even these laws carry a sense of calm. Because they say that black holes behave like ordinary physical systems, they have temperature, they have entropy, they have equilibrium states. This means that even though black holes are exotic objects, their behavior is not mysterious. It is quiet, predictable, and grounded in the same principles that govern everything else. When you imagine the horizon settling, cooling, preserving its simple shape, you may feel your own thoughts settling with it. Letting go of unnecessary details, letting go of noise, letting go of complications, until only the essential things remain. This mirroring between physics and experience is not accidental. The universe has a way of repeating patterns, of expressing the same ideas across different scales. And black holes are the ultimate expression of simplicity emerging from chaos. A collapsing star filled with storms and heat and motion, reduced to 3 parameters. A violent merger releasing bursts of gravitational energy, reduced to a quiet final shape. The noise fades, the ripples fade, the complexity fades, and what remains is a gravitational form so simple that it becomes soothing to even imagine. This section, this exploration of predictability, closes softly, but the journey continues, because around a black hole, time itself begins to behave in ways that are slow, relaxing, and strangely dreamlike. Time is usually something we treat as steady, a quiet background rhythm that never changes. Seconds feel like seconds, minutes feel like minutes, and the passing of time seems absolute. But near a black hole, this rhythm softens, stretches, slows, not violently, not suddenly, but gently, like a long exhale moving through space-time. This slowing of time is one of the most calming truths in all of physics, because it means that gravity is not just a force, but a shaping of reality that touches the flow of time itself. Time is woven into space-time, a dimension connected to the directions you can move in. And just as gravity curves space, it also curves time. Where the gravitational field is weak, time flows normally. Where gravity grows stronger, time runs more slowly. This slowing is not a metaphor, not an illusion, but a measurable effect. Your clock, your heartbeat, your thoughts, your entire sense of now would gently stretch if you were near a strong gravitational field. This is the essence of gravitational time dilation. Imagine drifting near a black hole, close enough to feel its influence, but far enough to remain safe. Time for you would flow slightly slower than it does for someone far away. Your seconds would stretch, your minutes would drift. You would not notice the difference locally, because your body and your mind would slow together. But from the outside, your motion, your signals, your heartbeat would appear to move with a delicate slowness, as if the universe were softly pulling at your moments. This effect becomes stronger as you move inward. Closer to the horizon, time stretches further. From far away, an observer would see you slow, dim, and gently freeze as you approach the event horizon. You would never appear to cross it. Your final image would hover just outside, fading. But this freezing is not happening to you. It is happening to the signals leaving you. Light trying to escape the gravitational well loses energy. Its wavelengths stretch, its colors drift to red, its motion slows, until the outside universe can no longer see you move. To you, the crossing remains uneventful. Time flows at its ordinary rhythm. Your clock ticks, your thoughts drift, your motion remains smooth. Nothing special happens locally. This contrast between what the outside sees and what you experience is one of the most softly dreamlike facts in general relativity. Two different truths existing at once, both correct, both natural, a duality caused by the way gravity shapes time. This is what makes the horizon so fascinating. It is not just a boundary in space, it is a boundary in time. From the outside, the horizon represents a place where time slows to an infinite standstill. From the inside, it is just another moment, another point in the flow of your own time. This contrast feels almost poetic, a reminder that time is not absolute. It is flexible, stretchable, responsive to gravity, and nowhere is it stretched more than near a black hole. The closer you get, the slower time flows. Imagine a spacecraft hovering near the horizon of a supermassive black hole. Far from it, hours pass normally, but near the horizon, those same hours become minutes or moments. A person who drifts near the black hole could return to find that years have passed elsewhere. Whole cycles of stars, seasons on planets, the shifting motions of galaxies, all moving forward while their own experience barely advanced. This stretching of time is not dramatic in the sense of fear. It is gentle, predictable, calm. Time simply stretches like a soft fabric being pulled. No tearing, no chaos, just the steady adjustment of space-time. And the reason time slows near a black hole is deeply mathematical. Gravity is curvature. Objects fall not because they are pulled, but because space-time leans inward, and time is part of that curvature. In regions where space-time is deeply curved, the flow of time slows, not because the clock breaks, but because the path through space-time becomes longer, deeper, slower. A black hole is the deepest curvature the universe allows, which means it is the place where time slows the most. Close your eyes and imagine time as a river. Far from a black hole, the river flows normally. Near the horizon, the current slows, thickens, stretches, until at the horizon from far away, the current appears to stop. But for someone within the river, the water still moves. The movement is internal, personal. This river-like behavior is not just imagery. It appears directly in the equations of relativity. The flow of time depends on the gravitational potential. Lower potential, slower time, and at the horizon the potential drops so far that time seems to pause. To an outside observer, this pause is infinite. To someone falling in it is simply seamless, another step in the journey downward. This dual perspective is one of the most soothing ideas in theoretical physics, because it reveals a universe that is not rigid, not fixed, but flexible, soft, responsive. Time is not a single ticking clock. It is a woven tapestry that bends gently under the influence of gravity. And as you imagine this bending of time around a black hole, you may notice something relaxing about the idea. The universe is not rushing. It allows time to slow, to stretch, to breathe. Even at its most extreme edges, nature moves with calm precision. Gravity shapes time the way it shapes space, smoothly, gradually, inevitably. And when you approach the deepest curvature, that smoothness continues. Time becomes slower, more fluid, almost dreamlike, like sinking into warm water, the flow around you growing quiet, and in this quiet, in this gentle stretching, you begin to see how relativity is not chaotic. It is soft, a set of rules that guide the universe with calm consistency. In the next part, you will drift deeper into this distortion, feeling how time behaves from different perspectives, until the entire concept unfolds gently before you, like a dream woven from physics. As you drift deeper into the idea of time slowing near a black hole, you begin to realize that time is not a rigid sequence of identical moments. It is fluid, elastic, quietly responsive to the shape of space-time. Gravity stretches time the way gentle pressure stretches a soft fabric. The stronger the gravity, the deeper the curvature, the slower the flow. This slowing does not feel strange to the one experiencing it. Your heartbeat, your breathing, your thoughts, all drift at the same rhythm as your local time. Everything internal moves together, so nothing feels distorted. But from far away, your time is seen differently. A distant observer watches your motions as if they occur through thicker air. Every signal you send takes longer to arrive. Every movement unfolds softly, slowly. Your descent toward the horizon appears to approach a kind of stillness, a slow fading spread out across eternity. And yet you yourself never feel this stretching. You experience smooth continuity. This duality between internal experience and external observation is one of the most dreamlike gifts of general relativity. Two perspectives woven into the same event, each valid, each anchored in the geometry of space-time. Imagine standing far from the black hole. You see your companions slow, dim, fade. Their signals turn redder, weaker. Their clock ticks slower. Their motions stretch across longer and longer intervals, until the very last moment before the horizon appears to freeze, suspended. But this freezing is not happening to them. It is happening to the light trying to climb out. The gravitational well pulls on the light waves, stretching them, slowing them, softening them, until the outside universe sees nothing more. This idea that light itself loses energy as it escapes is called gravitational redshift. It is a natural result of climbing upward in curved space-time, not violent, not dramatic, just a gradual draining of energy. The same way a ball slowly loses speed as it rolls uphill, except here it is light rolling up the slope of space-time. The deeper the slope, the greater the redshift. Near the horizon, the slope becomes infinite, which means light takes infinitely long to escape, and from far away you see a slow motion that never finishes, a moment spread into forever. This is why the horizon appears frozen from the outside, a perfect boundary shaped by time as much as by space. But locally, nothing freezes. Your descent continues. Time flows normally for you. Your clock ticks, your breathing moves, your thoughts drift. You do not see the horizon as a place where time stops. You see it as a moment like any other, a calm crossing, a continuation of your path. This difference between perspectives is not a contradiction. It is the natural outcome of time being woven into space-time. Every observer moves along their own thread, their own path, their own flow. And near a black hole, these flows diverge, softly, elegantly, inevitably. This divergence is one of the most relaxing ideas in all of physics, because it reveals that time is not universal, not absolute, but personal, shaped by gravity, shaped by motion, shaped by the path you take through the geometry of the universe. You carry your own time with you, a quiet companion, unchanged by the way others see you. Even the idea of infinite time at the horizon is not a physical barrier. It is a perspective, a coordinate choice, a way of measuring events from far away. But inside your own time, nothing diverges. Nothing becomes infinite. Everything remains finite, smooth, unfolding. This makes the event horizon a boundary of perception, a place where the fabric of time splits into different truths, a reminder that reality can be both absolute and relative. Absolute in the sense that the physics is consistent, relative in the sense that time depends on where you are. This relativity of time is not limited to black holes. Even on Earth, time flows slightly slower at sea level than it does on a mountain. Because the gravitational field is a bit stronger lower down, you do not notice it. But your clocks know, and satellites orbiting far above must account for the difference. Otherwise, their navigation signals would drift. Time dilation is already woven into daily life. Near a black hole, the effect is simply magnified, amplified, made visible in the most gentle and spectacular way. Imagine hovering just outside the horizon of a supermassive black hole. Time for you moves slowly, but you feel normal. You speak, you breathe, you think, and yet if you were to look outward, you would see the universe moving faster. Stars orbiting, galaxies drifting, cosmic events unfolding, all happening in a kind of accelerated motion. Because your time is slow, the universe moves around you. This idea creates one of the quietest images in all of astrophysics. A place where one could sit near the horizon and watch the future of the universe unfold. Not rapidly, not chaotically, but gently, as if the cosmos were quietly turning its pages. And as the universe ages, you would age slowly, your own moments stretching softly. This stretching is the heart of gravitational time dilation, a bending of the timeline as smooth as the bending of space. And in this bending, there is no violence, no tearing, only continuity, only curvature, only the gentle adjustment of the metric that defines spacetime. This softness is often overlooked, but it is one of the most relaxing truths in all of relativity. Time itself responds to gravity with grace. The flow adjusts, slows, stretches, but never breaks. And as you imagine this slowing of time, you may feel your own thoughts slowing, your own moments stretching, your mind drifting into the quiet. Because thinking about time near a black hole is like thinking about a dream where seconds become minutes, minutes become hours, and the boundaries between moments soften. When people imagine matter spiraling into a black hole, they often picture chaos, flames, violent collisions, violent twisting spirals of destruction. But the reality is far more elegant, far more structured, and surprisingly gentle when understood scientifically. An accretion disk is not a storm, it is an arrangement, a calm choreography created by gravity, angular momentum, and the quiet laws of orbital motion. Imagine countless particles, dust, gas, plasma, moving through space. Each particle arriving from a different direction, with a different speed. As they drift closer to the black hole, their paths begin to organize. Gravity guides them, nudges them, draws them inward, and any particle with the slightest sideways motion cannot fall straight in. Instead, it begins to orbit. Just like planets orbit stars, just like moons orbit planets. Curved paths defined by geometry, the particles circle, spiral, and gradually arrange themselves into a thin, flat structure, the accretion disk. A disk is not created by chaos, but by order, by the conservation of angular momentum, a law that says rotation cannot simply vanish. If matter carries even a small amount of sideways motion, gravity preserves it. The result is a smooth disk gathering around the black hole. Not a tornado, not a whirlpool, a cosmic ring obeying calm, predictable physics. The inner regions of the disk orbit faster than the outer regions. This difference in speed creates friction, but not friction in the everyday sense. It is a subtle exchange of angular momentum, a gentle rubbing between layers of orbiting gas. This friction produces heat, not violently, but gradually. As the gas warms, it begins to glow, often in soft X-rays, sometimes in visible light, depending on the temperature. This glow is not fire, it is thermal radiation, the same kind of glow that comes from any warm object in the universe. The same principle that warms planets, that lights the surface of stars. The disk shines because it is warm, not because it is burning. And this warmth arises entirely from motion, from the slow, steady downward drift through the curved spacetime. As the particles lose energy, they spiral inward. Their orbits shrink, their paths tighten, until eventually they reach a point where stable orbits no longer exist. That point is called the innermost stable circular orbit. Beyond it, the spiral steepens, not violently, but inevitably, as if the curvature of space-time were gently guiding the matter toward the horizon. Everything in the accretion disk follows lawful motion. Nothing is random, nothing is chaotic. The patterns are predictable, the structure is stable. A disk can persist for millions of years, fed by interstellar gas, or shredded stars, or drifting clouds drawn in by gravity. But regardless of the source, the behavior is the same. Matter enters, energy is radiated, and the disk settles into equilibrium. Even the magnetic fields threading through the disk contribute to the order. They help move angular momentum outward, allowing matter to spiral inward. This magnetic coupling is not turbulent. It has rhythm, quiet, mathematical rhythm, a slow unwinding, like a very gentle turning of invisible gears. Magnetic fields can also create jets, tall columns of energy launched upward from the poles. These jets look dramatic, but even they arise from stable physics. Twisted magnetic field lines channel energy and guide particles into narrow beams. The beams are not explosions, they are emissions, structured, guided, and maintained by the spinning geometry of the black hole. Everything in the accretion environment follows rules, and because the rules are consistent, the disk behaves like a quiet machine, a machine that converts gravitational energy into light, soft light, steady light. Even the variability of the disk's brightness is governed by physics. Sometimes the flow thickens, sometimes it thins, but every change has a cause, a shift in density, a ripple of magnetic pressure, a patch of hotter plasma drifting around the orbit. These fluctuations are not chaotic, they are patterned. Patterns astronomers can measure, predict, and model. This predictability is part of what makes accretion disks so soothing to think about. You can imagine them as cosmic rivers, flowing, glowing, changing shape only in ways allowed by physics. Their spiral motion is not frantic, it is gradual. Matter orbits millions of times before it finally falls in, each orbit carrying away just a bit more energy, a slow descent, a gentle unwinding. Even the temperature changes smoothly, hotter toward the center, cooler toward the edges, like the gentle gradient of a star's atmosphere. No shocks, no turbulence, just smooth physics. And when the matter reaches the inner edge of the disk, it takes one last orbit, then crosses the boundary into the plunge region, where the spiral can no longer hold. The downward motion deepens, the path steepens, but the transition is not a crash, it is simply the natural continuation of orbital decay, a final drift through spacetime into the horizon. The disk feels none of this directly. It simply continues to orbit, shine, and flow. The black hole absorbs the inward matter without a ripple, and the outer disk keeps spinning, calm, steady, sustained. This entire process is elegant, a dance, a slow, gravitational waltz that plays out on cosmic scales. And when you imagine this silent rotation, glowing softly, moving with gentle predictability, you may feel your own mind following that spiral, letting thoughts circle, slow, and drift inward, toward quiet, toward rest, toward the center of your own stillness. And in the next part, you will drift even deeper, into the gentle physics of falling inward, and what happens once you cross the horizon. If you imagine the accretion disk as a kind of cosmic river, then this part of the journey is where that river reveals its deeper patterns. Because even though the disk glows, even though it rotates, even though it gradually shifts from orbiting matter to inward-moving matter, everything it does remains anchored in peaceful, predictable physics. And the more closely we look at the motion of this disk, the more we see that its behavior is not chaotic at all. It is almost meditative, a repeating pattern, a steady cycle, a slow transformation from gravitational energy into light. One of the most soothing truths about accretion disks is that their spiral motion is not a tumble. It is not a fall. It is a gradual loss of orbital energy, a soft letting go. Every particle gives up a tiny fraction of its energy during each orbit, and that lost energy appears as heat, a quiet conversion, lawful, predictable, orbit after orbit, millions of rotations, until the matter has released enough energy to take the next step inward. This inward drift is not forced, it is earned. The particle moves closer to the center only when it has released the necessary energy. The disk is a kind of cosmic balance sheet. Energy flows out as light, angular momentum flows outward, matter flows inward, everything is conserved, everything accounted for. This conservation creates the stability of the disk. The same laws that govern planets orbiting stars govern these spirals too. The only difference is the scale. But the laws are the same. The disk shines because it is warm, but even this warmth follows a smooth gradient. The outer regions are cooler. They glow faintly, softly. The inner regions are warm enough to emit X-rays, but even this glow is gentle when described scientifically. It is not a roar, it is a whisper, a thermal whisper from matter that has lost energy to the gravitational well, not burned, not melted, just warmed. And even that warmth is temporary. Once the matter falls through the inner edge of the disk, it no longer produces light. It becomes silent, invisible, crossing the horizon in complete quiet. In that sense, the accretion disk is like a glowing halo, a ring of warm material surrounding a region of perfect darkness, a luminous boundary, a soft outer layer of a space-time well, a place where matter shines as it transitions from orbital energy to gravitational rest. But even more beautiful than the glow is the organization. The disk's structure is shaped by the equation of motion known as the Kerr metric if the black hole spins. This metric predicts the orbits, the shape of space-time, the speed of particles, the specific radii at which the motion changes. Every orbit has a precise frequency. Every path inward has a calculable rate. Nothing is random. And because of the black hole's rotation, space-time itself twists. This twist, called frame dragging, causes the inner disk to be pulled forward, stretched gently. This stretching is not chaotic, it is steady. It adds a slight lean to the orbits, a slant that is measurable, predictable, and poetic in its subtlety. Even the variations in brightness called quasi-periodic oscillations come from this geometry. They are not noise. They are signatures, patterns of motion that arise when matter interacts with curved spacetime. These oscillations tell us the spin of the black hole, the exact radius of the inner orbit, the distribution of energy. Every flicker, every variation is structured, a message from the physics of the disk. This is why astronomers can measure the spin of a black hole just by listening to the soft X-ray hum of its accretion disk. The frequencies are a fingerprint, unique, precise, and deeply tied to the geometry. This connection between sound-like oscillations and space-time curvature is incredibly calming, because it means that even in extremes the universe keeps its rhythm. A black hole may be powerful, but it moves with consistency, with order, with a quiet stability that never fades. And the accretion disk echoes that stability, orbit after orbit, light after light, until the matter settles inward. Even magnetic turbulence, which sounds chaotic in everyday language, is shaped by physical laws. The magnetorotational instability guides energy outward, creates smooth flow, and allows the disk to maintain its structure. This process does not feel like turbulence when understood scientifically. It is a gentle sorting, a redistribution. Magnetic fields connect different layers of the disk. They help the outer material gain angular momentum. They help the inner material lose angular momentum. The result is a slow, steady drift, a long, patient inhale into the black hole, a flow that continues as long as matter is available, and even the jets, thin beams launched from the poles, are orderly. Guided by magnetic fields, powered by rotation, collimated by geometry, they do not explode outward. They stream, silent, straight, consistent. Particles near the poles are guided outward while particles in the disk flow inward. Two motions, opposite directions, both governed by the same equations, all tied together by the spinning geometry of spacetime. This coupling between inward motion and outward jets is one of the most elegant mechanisms in astrophysics. It shows that even when energy is expelled, it follows a structure defined by rotation, charge, and magnetic fields. A structure so precise that the jets remain narrow across thousands of light years, a pencil-thin beam crossing interstellar space. Yet born from simple physics, all of this reveals the deeper truth about accretion disks. They are not turbulent furnaces. They are cosmic engines, governed by symmetry, shaped by gravity, illuminated by heat, organized by motion. And when you imagine their endless spiral, their glow, their predictable rhythms, you may feel yourself spiraling too, not downward, but inward, toward the still center of your own awareness, toward calm, toward quiet, toward rest. And as the accretion disk settles into a steady radiance, you may gently drift into the next section, where the journey crosses the horizon and the falling motion becomes part of the geometry itself. Falling into a black hole is one of the most misunderstood ideas in all of physics. People imagine tearing, stretching, shredding. They imagine violence. But when you look at the equations, when you look at the geometry, when you look at how gravity actually behaves, you find something very different. You find calm. You find smoothness. You find a journey that unfolds gently, quietly, with no sudden boundary and no physical barrier. The experience of falling into a black hole depends almost entirely on one thing: its size. A small black hole has a strong tidal gradient near the horizon, meaning that gravity changes rapidly from your head to your feet. But a large black hole, a supermassive black hole, has a tidal gradient so gentle that you could drift inward without feeling anything unusual. This difference is one of the most soothing truths about black holes. The larger they become, the gentler their horizons become. Imagine drifting toward a supermassive black hole millions of times the mass of the sun. The horizon could be larger than an entire solar system. And the tidal forces that you feel at the boundary are small, smaller than what you feel standing on Earth. The surface of our planet pulls more strongly on your feet than a supermassive black hole's horizon pulls on your whole body. This idea softens everything, because it reveals that the horizon is not a wall. It is not a boundary you crash into. It is only a region where escape becomes impossible, not because of a physical surface, but because of geometry. Gravity curves spacetime inward, and at the horizon all paths lead deeper into the curvature. That is all. Falling inward feels completely normal. Your motion is free fall. Free fall is weightlessness. It is the same feeling astronauts experience in orbit. Smooth, gentle, effortless. This is why falling into a large black hole would feel like floating through curved space-time, the most extreme gravity in the universe, and yet experienced as gentle descent. The idea that nothing special happens at the horizon is one of the most calming ideas in relativity, because it tells us that physics remains smooth, consistent, predictable, even at the threshold of the unknown. Nothing tears, nothing snaps, nothing distorts abruptly. You simply follow a geodesic, the natural path through space-time, the same way a planet follows its orbit, the same way a comet follows its long arc. You become part of the space-time curvature, guided without effort, carried without struggle. You drift. And because the tidal gradient is gentle in a supermassive black hole, your body, your atoms, your molecular structure would remain intact for a very long time. Only deep inside, where the curvature grows rapidly, would stretching become significant. But this is far past the horizon, far deeper than most people imagine. And the journey there is slower, quieter, softer than any dramatic image suggests. The idea of spaghettification, often used in popular descriptions, is dramatic, but the physics is gradual, a slow increase in the difference between gravitational pull on one part of your body and another, and in a large black hole that gradient is almost undetectable at the horizon. You cross without noticing, you cross without pain, you cross without any signal from your senses. To you, nothing special happens. Your time continues normally. Your motion remains smooth. Your awareness remains continuous. The crossing is a quiet passage, just another step in the inward journey. Outside observers never see you cross, but that is their perspective, not yours. The external image is stretched by time dilation, slowed, dimmed, faded, but your own experience is peaceful, unbroken. This duality between perspectives is one of the most dreamlike aspects of black holes. From the outside you freeze, from your own frame you drift, and the drifting is calm. As you move deeper, the curvature grows, but it grows smoothly. No sudden spike, no sudden jolt, just a slow deepening of the inward pull, a gentle narrowing of the available paths, space-time becoming more curved, more focused, more directed, and your geodesic responds, following the natural curve. This is the essence of falling in. Not destruction, but continuation. Not violence, but geometry. Your path is defined by the metric. Your motion is defined by curvature. Your experience is defined by free fall, and free fall is always weightless. The classical picture of being pulled apart is only true for very small black holes, and even then it is not immediate. It is a gradual increase in tidal forces, the difference between the gravitational pull on your feet and your head. But again, this is not a sudden tearing. It is a gradient, a slope, the same gentle slope that shapes all gravitational effects, just steeper and more pronounced. But still smooth, always smooth. General relativity does not allow discontinuities. Space-time remains continuous. Curvature remains finite at the horizon. Everything that happens there is gentle. The horizon is not dangerous. It is simply a causal boundary, a place beyond which light cannot return. But crossing it is no more violent than crossing a line on the floor. It is the boundary that changes, not you. And once crossed, your journey continues. Into regions where physics is still defined, where motion still follows equations, where your path is still a geodesic. Even deeper, where tidal forces grow stronger, you continue to fall. But fall is not the right word. You are not plummeting. You are following space-time. You are flowing like a river following the shape of its valley. The valley deepens, the slope increases, but the flow is continuous. No breaks, no shocks, just smooth descent. This is why falling into a black hole is one of the calmest processes in theoretical physics. So calm that your body would not register the difference between falling toward a black hole and floating in empty space. Because both are free fall. Both are weightlessness. Both are geodesics. And as you imagine this inward drift, you may feel your own mind soften. You may feel yourself let go of resistance. You may feel gravity's metaphorical pull, drawing you inward, gently, smoothly, toward quiet, toward stillness, toward rest. The deeper you imagine drifting into a black hole, the clearer it becomes that almost everything people fear about this journey comes from misunderstanding, because the truth, the scientific truth, is far softer and far more elegant than any dramatic image suggests. Once you pass the horizon in a large black hole, you are still in free fall. And free fall is a state of perfect calm, a state where you feel no weight, no force, no pressure, just motion, guided entirely by the curvature of spacetime. This inward motion is not a plunge. It is not a crash. It is a continuation, a smooth following of the natural path that spacetime creates. You move because spacetime itself is guiding you, and the guiding is gentle. As you drift inward, you may imagine gravity strengthening, but gravity is not a force pulling you downward. It is the shape of the world around you. You are not being dragged, you are gliding. Like a leaf following the curve of a slow-moving stream, the deeper you go, the more the stream bends. But the bending is continuous, no sudden changes, no abrupt jolts. Inside the horizon, all geodesics point inward. Every path you could take leads deeper into spacetime, not because something pushes you, but because the geometry leaves no other direction. This inevitability is peaceful. There is no choice to make, no struggle to resist. You are carried by the shape of the universe. Even the idea of stretching, the tidal force, remains gentle for a long time. In a supermassive black hole, millions or billions of times the mass of the sun, the tidal forces are weaker than Earth's gravity until you are extremely deep inside, weaker than the pull keeping your feet on the ground. This means that the classical image of being torn apart at the horizon is not accurate. For large black holes, the horizon is one of the safest regions. You still have time, space, awareness. There is no pain, there is no tearing, there is only descent, smooth, inevitable, quiet. Even as you fall, you could look outward and see the universe behaving in unusual ways. Time outside would seem to rush forward, stars would drift, galaxies would shift, cosmic events would unfold more quickly, because your time is slowed. This difference in time flow gives the inward journey a dreamlike quality, a sense that you are witnessing a fast-forwarded universe. But inside your own frame, nothing feels unusual. Your heart, your breathing, your thoughts continue normally. Your sense of time remains familiar. It is only when you compare your experience to the outside universe that the distortion appears. But comparison is a distant concept. Inside the fall, there is only motion, continuity, flow. Nothing breaks, nothing stops. You drift, and eventually you reach a region where the curvature begins to grow more rapidly. The tidal gradient increases, but even this happens gradually. You do not encounter a sudden wall of force. The stretching increases smoothly, a gentle slope turning steeper, but not instantly, not violently. This is one of the most important and calming truths about black holes. General relativity does not allow sharp edges. The curvature of spacetime is always continuous. Tidal forces rise gradually. The deeper the fall, the more pronounced the stretching. But every change is smooth, predictable, mathematically elegant. At some depth, the tidal forces would become strong enough to overcome structural integrity. Atoms, molecules, cells would begin to feel different gravitational pulls. But this point is far inside, far beyond the horizon, far deeper than most descriptions ever mention. And even when this region is finally reached, the process is not an explosion. It is the continuation of stretching, a final unwinding of matter under extreme curvature. But before this point, the journey is tranquil, soft, unbroken, a glide through a region where spacetime has no outward directions. Only in and in and in. Many people imagine a crushing force from all sides, but crushing is the wrong picture. Gravity inside a black hole is not a squeeze, it is a direction. A path, a flow, not pressure, not compression, just guidance. Your entire motion is a following the lines of curved spacetime, lines that bend inward. As you move deeper and the curvature strengthens, you may imagine this inward pull as a narrowing funnel. But the funnel is not physical. It is geometric, a shape described by equations, smooth, continuous, inevitable. And as you drift downward, you might imagine the outside universe becoming harder to see. Not because darkness closes in, but because spacetime stretches the light. The wavelengths grow longer, colors fade, images distort. Eventually the outside world slips away. Not suddenly, gradually, softly, like a memory drifting out of reach. Your awareness remains, your motion continues, your time flows. But contact with the wider universe has ended. Inside the horizon, everything you experience belongs to the interior geometry, an inner world defined by curvature, where every path leads deeper and deeper, toward a region where classical physics can no longer describe what happens. This is where quantum gravity would take over. But no one has the full theory yet. And so your journey inward passes gently into mystery, not fear, not chaos, just mystery. A region where our equations are no longer complete, a region where the universe keeps its secrets. But from your perspective, even this transition feels soft, because the equations that fail are the equations we use, not the laws of nature acting on you. Nature has its own continuity, its own consistency, its own calm. And as you drift toward this deeper region, the quiet becomes fuller, deeper, more complete. The outer universe has slipped away, only space-time remains, carrying you, guiding you, enfolding you, weightless, timeless, pulled forward only by geometry. And as this section closes, you may gently feel your awareness settle, because the next part will take you outward again, not into escape, but into scale, into the ancient, quiet giants that rest at the hearts of galaxies, where gravity shapes entire worlds, not through violence, but through calm, enduring presence. Nearly every large galaxy in the universe, including the one we live in, has a supermassive black hole resting quietly at its center. Not raging, not devouring, not tearing the galaxy apart, but sitting there, silent, stable, ancient, a gravitational anchor older than the stars that orbit it, a calm presence that shapes the motion of billions of suns. And when you imagine this, a black hole millions or billions of times the mass of the sun, you might expect chaos. But the truth is the opposite. The larger the black hole, the gentler its horizon becomes. Its pull spreads smoothly across a vast region of space, its influence extends gracefully through the galaxy, and its presence is not destructive. It is structural. Galaxies form around them, grow around them, stabilize around them, like a wheel built around a central hub, or a city built around a quiet, ancient plaza. Supermassive black holes do not tear galaxies apart. They help hold them together, they add weight to the central region, deepening the gravitational well, guiding the rotation of stars and gas. This guidance is calm, slow, measured. The stars do not spiral inward uncontrollably. They orbit for billions of years, following the same slow arcs, the same cycles, and the black hole remains at the center, not chasing, not pulling violently, simply shaping. Its gravity is not a shout, it is a steady tone, soft, constant, enduring. Even the way it grows is gentler than people imagine. Supermassive black holes do not swallow stars one after another in rapid succession. They grow slowly, steadily. A star may fall in once every few thousand years. A cloud of gas may drift inward once every million. Most of the time, they are quiet, still, almost dormant. This stillness is important because it tells us that the universe's great structures are not driven by constant violence. They are driven by long periods of calm, by slow accumulation, by steady gravity. And if you imagine the central region of a galaxy, you might picture turbulence, but step back and you see something different. Stars orbit in smooth, predictable paths. Gas circles in vast curves, magnetic fields arc gently through the interstellar medium. Everything is shaped by the same central mass. Everything moves in response to the geometry it creates, and the geometry is smooth. The gravitational well is deep, but it is also wide. The tidal forces are incredibly weak across human scales. That is one of the most surprising and calming truths about supermassive black holes. If you were falling toward a small black hole, the change in gravity across your body would be large. But if you fell toward the supermassive black hole at the center of the Milky Way, you would feel nothing. Nothing at the horizon, nothing at the crossing. Not even the faintest stretch, because the tidal gradient is extremely small, so small that you would pass through the event horizon as gently as drifting through darkness. This gentleness tells us something profound. The most massive black holes are the calmest, the quietest, the least hostile. They are like massive oceans compared to small, choppy lakes, deep, vast, placid. This calm extends to the entire galaxy. Because the gravity of the central black hole helps stabilize the motions of stars. Without it, the galactic core would be looser, less anchored. With it, the central region has weight, structure, consistency. Even the Milky Way owes part of its ordered motion to its central black hole. 4 million suns worth of mass, resting quietly, invisible, but essential. And when stars pass nearby, most of them do not fall in. They swing around. They continue their orbits. The black hole doesn't swallow them. Its event horizon is tiny compared to the space around it. Most stars have no interaction at all, they simply feel its presence. A distant, steady pull, like a lighthouse guiding ships with its quiet, unchanging glow. The black hole rarely feeds. Most of the time it rests, shrouded in darkness, not because it hides, but because it emits no light. A perfect gravitational lantern with no flame, yet its influence spreads through the galaxy, subtle, soft, powerful, and around it the central stars form a dense cluster. Their orbits are some of the most beautiful paths in astronomy. Curved lines, slow arcs, ellipses that shift in response to unseen mass. And from these orbits we know the black hole is there, not from its light, but from the stars that dance around it. This dance is not frantic, it is orderly. Every star moves according to gravity. Every orbit follows the equations. The black hole is the conductor, the stars are the instruments, the galaxy is the symphony, and the music is gravity, soft, steady, cosmic. And even when a star does drift too close, its fate is not instant. It is stretched, heated, and turned into a stream of gas, a tidal disruption event. But even these rare events follow predictable patterns. Their light curves, their spectra, their timing, all unfolding according to physics, not chaos. This predictability is the quiet beauty of supermassive black holes. Their behavior is not random. It is governed by equations, equations that scientists know well, equations that remain smooth even at the edge of the unknown. And as you imagine these enormous objects, their slow growth, their calm influence, their ancient presence, you may begin to feel some of that calm settle into you. The idea that even the most massive, most extreme objects in the universe can be sources of stillness, of order, of structure, of quiet. And in the next part, we will continue this gentle path, moving even deeper into the mystery, exploring what it means to reach the boundary where knowledge ends and curiosity begins. When you picture a supermassive black hole resting at the heart of a galaxy, it is easy to imagine something fierce. But the truth is vastly calmer. The black hole does not churn the galaxy, it steadies it. It does not cling to stars with violent force. It simply shapes their orbits, quietly, patiently, over timescales so long they feel like the deep breathing of the universe itself. And one of the most soothing facts about supermassive black holes is how slowly they grow. They do not devour constantly. They do not inhale the galaxy around them. Most of the time they are almost entirely still, dormant, asleep. For every million years they may feed only briefly, a passing cloud, a wandering star, a trickle of gas from the galaxy's inner ring. Even during these moments of feeding, their behavior is orderly. Matter spirals in through the accretion disk, releasing energy in predictable patterns. And when the flow ends, the disk dims, and the black hole becomes silent again. These long pauses tell us something profound. Supermassive black holes are not engines of destruction. They are reservoirs of gravity, stable anchors in the geometry of the galaxy. Imagine the Milky Way, 200 billion stars, dark matter, dust, gas, spiraling in giant waves, and in the center a single mass 4 million times the mass of the Sun. Silent, unlit, steady. Its gravitational well gives the central bulge its weight. It helps maintain the rotation curve of the galaxy. It shapes the orbits of the oldest stars. And despite its enormous mass, its event horizon is tiny, so small that a beam of light could cross it in minutes. Compared to the galaxy, it is a grain of sand in a vast desert, but a grain with incredible density, perfect symmetry, and deep gravitational influence. The stars closest to it, the so-called S-stars, orbit with extraordinary precision. Their paths trace gentle ellipses, sweeping around the invisible center. And from these orbits, astronomers can measure the mass of the central black hole with astonishing accuracy. The stars themselves are the observers. Their motion is the evidence, and what they reveal is not chaos, but perfect order. The center of the galaxy is not a storm. It is a well, a smooth, quiet well curved into spacetime, so well defined that even the fastest moving stars follow predictable paths. This predictability is comforting, because it means that even in regions of extreme gravity, the universe stays lawful, symmetrical, calm. And over billions of years, the black hole's presence helps regulate the flow of gas in the central region. When the galaxy is young, gas flows inward easily. This gas can ignite star formation, or settle into a disk, or slowly feed the central black hole. When this happens, the black hole brightens, but even the brightness follows rules. Quasars, The most luminous phase a supermassive black hole can enter are not explosions. They are simply accretion disks shining intensely. Light produced by matter losing orbital energy. Even the most brilliant quasar is governed by stable physics. A quasar is just a black hole with a very bright halo, and that brightness can last for millions of years. But eventually the gas thins, the light fades, the accretion stops, and the black hole returns to stillness. This cycle is patient. Measured cosmic, most galaxies go through it only once or twice, and afterward the black hole lives in quiet. Dark, almost invisible, but always present, a silent anchor in the galactic core. Even galaxies that collide carry their black holes toward one another. Slowly, over millions of years, and eventually the black holes merge, not explosively, but in a final gravitational embrace, releasing gravitational waves that ripple gently through space-time, a soft echo of a massive event. Then the galaxy's center reestablishes equilibrium. A new black hole forms, more massive than before, but just as quiet, and the galaxy continues. Stars orbit, gas flows, the spiral arms turn. Life, in the cosmic sense, goes on. Many people picture black holes as destroyers, but supermassive black holes are more like foundations. A galaxy without one would be less stable, less orderly, its inner regions less coherent. The black hole gives structure, weight, balance, and because their growth is slow, their influence steady, their behavior predictable. They embody a kind of cosmic patience, a kind of ancient calm. Imagine drifting near the center of a galaxy, far from the bright glow of star-forming regions, where stars are older, denser, and orbit with quiet precision. You drift in this place, where the pull of the black hole is gentle, where the tidal forces are mild, where the deepest part of space-time's curvature feels like a smooth valley. Not a cliff, not a trap, just shape, geometry. A place where motion unfolds slowly, peacefully, predictably. And in that image there is something soothing, because the universe is vast and filled with extremes. But even in those extremes there is order, there is quiet, there is structure. Supermassive black holes remind us that the deepest forces in the cosmos do not need to shout. They can act with silent influence, with steady gravity, with gentle arcs of stellar motion, with a calm center around which everything else turns. And as this part ends, you may feel some of that stillness settle over you, the sense that even the most powerful objects can be peaceful. And in the next section, you'll drift into a deeper mystery, not about falling, not about structure, but about the edge of what we can know, where light cannot return, and questions cannot reach past the horizon. There is a place around every black hole where knowledge, in the strictest scientific sense, can go no farther. A boundary not of matter, not of energy, not of anything physical, but a boundary of information, the event horizon, not a surface you can touch, not a membrane, not a wall, but a limit on what the universe will ever allow us to observe. And this limit is not frightening when described softly, it is peaceful. A quiet edge where the known fades into the unknowable, a threshold where questions cannot return. And because of this, the horizon is not just a physical boundary, it is a conceptual one. A place where physics meets silence, where measurement meets darkness, where observation meets patience. Even the most powerful telescopes cannot look past it. Not because the region inside is chaotic, but because light cannot escape. Information cannot climb out of the curved geometry. The horizon is the boundary between what can be observed and what forever remains internal. And this boundary is soft, smooth, perfectly shaped by the geometry of space-time. When matter falls inward, it crosses the horizon without noticing. No signal, no sound, no resistance. It simply drifts past the point where returning becomes impossible. But from the outside, the story is different. An external observer would see the falling object slow, dim, fade, never quite reaching the horizon, not because it stops, but because time dilation stretches its motion infinitely. The object's light becomes redder, fainter. Waves of light stretch so much they slip beyond detection, and to an observer waiting far away, the object never crosses. This dual perspective is one of the quiet mysteries of relativity. To the falling traveler, the horizon offers no resistance. To the outside universe, the traveler seems suspended forever. Frozen at the edge, like a memory held in light. This contradiction is not a flaw. It is the nature of perspective in curved space-time. Two truths coexisting, both correct, both peaceful. And at the heart of these truths lies the idea that the horizon represents not a physical barrier, but a boundary of information. The universe keeps some regions sealed, not maliciously, but simply because the geometry does not allow light to escape. Inside the horizon, all paths lead further in. Outside, some paths lead away. The horizon separates these regions, a line drawn by geometry, soft, precise, absolute. This boundary creates a deep sense of wonder, because everything inside becomes hidden, not destroyed, not erased, just unobservable, wrapped in the darkness of curved spacetime. Even the shape of the interior is unknown. Our equations predict some aspects, but not all. Classical relativity gives us one picture. Quantum physics gives us hints of another, yet the truth remains out of reach, not because we lack tools, but because the information cannot return. This makes the horizon a quiet teacher. It reminds us that the universe is not obligated to reveal everything. Some places remain forever silent. Some mysteries remain forever inward. And this silence is not unsettling. It is soothing, because it shows that knowledge has natural boundaries. That curiosity will always have room to grow, that the universe contains depths beyond any measurement. Another calming idea is that the horizon is perfectly smooth, even when the black hole spins, even when it charges. Even when matter falls across it, the horizon does not ripple, does not twist, does not snap. It is stable. The geometry adjusts, but always returns to perfect shape. A smooth sphere if the black hole is still, a slight oblate curve if the black hole spins, but always a well-defined boundary. No cracks, no disturbances. Even gravitational waves do not disrupt it. The horizon absorbs them, settles, and becomes smooth again. This stability is calming, because it means that black holes are not unpredictable. Their horizons stay orderly even in extremes. And on this still surface, though nothing physical sits there, we imagine the meeting point between worlds. The inside world where paths all lead deeper, and the outside world where light can still escape. The horizon separates them. A perfect edge, a mathematical boundary, a quiet line between observable physics and hidden physics. And in this idea there is a kind of peace. Because the universe is vast, and we know so much, but not everything. There will always be questions that remain inside the horizon, out of reach, gentle reminders of the universe's depth. Even the information paradox, the question of whether information is lost forever inside, is a quiet puzzle, a soft tension between quantum theory and classical geometry. Not a crisis, just a whisper from the boundary that we have not yet heard the full story. Some theories say information escapes slowly through Hawking radiation. Others suggest the horizon stores information in subtle quantum patterns. Others imagine a deeper structure of spacetime. But none of these ideas disrupt the calm, because the horizon remains stable, smooth, unbroken, a symbol of the universe's quiet mysteries. And as you imagine that perfectly curved boundary, glowing softly in the fabric of spacetime, you may feel a sense of release. A realization that mystery is not something to fear. It is something to rest within, something that lets the mind drift. Knowing that not everything needs to be explained tonight, the horizon holds its silence, and you can drift gently into the next part, where the black hole whispers energy back into the universe, over timescales longer than galaxies, longer than stars, longer than the age of the cosmos itself. The horizon, the quiet boundary of a black hole, is one of the most peaceful ideas in physics when you let it unfold slowly, because it is not a violent edge, not a cliff, not a tearing boundary. It is simply the place where information stops being able to climb back out, a limit imposed not by force, but by geometry, by the shape of spacetime itself. And the more gently we think about it, the more beautiful this boundary becomes. Imagine standing far from a black hole, watching an object drift inward. It moves normally at first, then slowly, then more slowly, and eventually its motion seems to freeze, suspended at the edge, never quite crossing, its light stretching, reddening, fading, until it disappears into wavelengths too long for any instrument to detect. The object seems to linger, as if the horizon were holding it, but nothing holds it. It is simply the warping of time. Time outside the black hole, and time near the horizon flowing differently. The closer the object gets, the more slowly its light reaches you. Not because the object slows, but because the time it experiences is different from the time you experience. Two clocks, two rhythms, two realities coexisting, softly, peacefully. To the object itself there is no pause, no slowing. It crosses the horizon as effortlessly as drifting through darkness. The boundary is invisible, intangible. Just a mathematical line in space-time, no more solid than a shadow. And that alone makes the horizon something soft, something quiet, a place defined not by force but by perspective. A difference in how observers experience time. This is one of the most soothing lessons general relativity offers, that two perspectives can both be right, that reality can depend on where you are, and that this dependence is not chaotic, it is structured, predictable. Curved spacetime gives each observer a valid view, even if those views cannot be reconciled. This idea creates a kind of calm, because it reminds us that the horizon is not a place of failure. It is a place where physics reveals its depth, a place where the laws of nature stretch our intuition but remain smooth, continuous, unbroken. Another quiet truth about the horizon is that nothing inside ever sends a message back. Not because something blocks it, but because the geometry of spacetime tilts all paths inward. There is no outward direction, no escape trajectory, no way to curve a photon's path back across the boundary. This is not a punishment, it is simply the way curvature works. The same way a valley guides water, the same way a canyon guides wind. Inside the horizon, the downhill direction is always deeper inside, not physically downhill, geometrically downhill, a slope in the fabric of spacetime, smooth, steady. Absolute. This absolute inwardness is quiet, certain, a natural end to the outward possibilities, and that natural end creates a conceptual boundary, not a crisis, just a limit. We reach an edge beyond which observation cannot continue, a horizon not just in space but in understanding, and when you sit with that idea, when you allow it to settle gently, it becomes comforting. A reminder that not everything must be known, that the universe contains mysteries that are meant to stay mysterious, at least for now. Perhaps the deepest mystery connected to the horizon is the question of information. Quantum mechanics tells us that information cannot be destroyed. General relativity tells us that the horizon hides information permanently. Two truths, side by side, one saying nothing is lost, the other saying nothing can return. At first this may seem like conflict, but when explained slowly, it becomes a kind of softness, an invitation, a reminder that our theories are not complete, that nature may have a deeper layer, a quiet truth beneath the equations. Some physicists imagine information stored on the horizon itself, encoded in quantum patterns. Others imagine that information escapes through Hawking radiation, gradually, very gradually, across timescales so long they stretch meaningfully beyond any human concept of duration. Others imagine that space and time have a deeper structure, something woven, something holographic, something not yet visible. But none of these ideas break the horizon's calm, because every version preserves the smoothness, the elegance, the quiet geometry that defines the boundary. The horizon remains stable, predictable, silent. Even in quantum models, it remains a place of gentle mystery, a membrane of information, a limit of observation, a boundary of return, but never a barrier, never a wall, just a threshold, a quiet line between what can be seen and what forever drifts into the deeper interior. And when you imagine that threshold, perfectly curved, perfectly smooth, held by nothing except the shape of spacetime, it almost feels like a place where thoughts can rest, where questions can pause, where curiosity can breathe. Because the horizon does not demand answers. It invites wonder, it invites stillness. It invites you to accept that some things remain beyond reach, not in a frightening way, in a peaceful one. A reminder that the universe is larger than our comprehension, older than our physics, deeper than our tools, and that it will always hold regions where silence prevails. And as you rest within that silence, you drift naturally into the next part, where the black hole begins its slow return of energy to the universe, not violently, but softly, quietly, over timescales so long they become a lullaby of cosmic duration. The universe becomes very quiet when you let your thoughts drift toward the idea of a black hole, not the frightening version from movies or stories, but the real one, the scientific one, the one shaped by the smooth curvature of spacetime, the one defined by equations so elegant they feel almost like meditation. After exploring so many ideas tonight, the calm geometry, the simplicity, the stretching of time, the graceful spiral of accretion disks, the gentle fall across a horizon, the ancient weight of supermassive giants, the mysterious boundary between what can return and what cannot. You might notice something. None of these ideas end in chaos. None of them are violent. Everything about a black hole is steadier, softer, more predictable than people imagine. And that is where the quiet beauty lies. Because when you strip away the dramatic visuals, the misconceptions, the imagined explosions, what you find is a structure governed by calm rules, gravity bending inward in the smoothest possible way, time stretching with perfect continuity, motion following natural geodesics, the simplest paths available to spacetime. Even the horizon itself is calm, a surface not made of matter, not made of energy, just a boundary in geometry, a place where outward light cannot climb, where the slope of spacetime tilts entirely inward, not violently, just inevitably. As if the universe whispers a quiet direction, and everything gently follows. When you think about it slowly, when you let the idea settle, it becomes almost soothing. A black hole is a place where complexity disappears, where noise becomes silence, where all information is compressed into the simplest possible form. Mass, spin, charge, 3 numbers, 3 quiet descriptors. Everything else fades from the outside world, all the chaotic details of the star that collapsed, all the turbulent processes of its earlier life, all the intricate structures that once existed. They're no longer visible. Only the essentials remain. As if the universe removes the unnecessary and leaves behind a perfect, minimal object. It is rare in nature to find something that becomes simpler as it becomes more extreme. And yet black holes do exactly that. They are the quietest endpoints of gravitational evolution. Nothing else in the cosmos achieves such purity. Not stars, not galaxies, not nebulae, only black holes. And that simplicity gives them a strange kind of peace. Because simplicity is predictable. Simplicity is stable. Simplicity is calm. When a black hole forms, it settles. It rings like a bell of space-time. Tiny distortions, ripples, vibrations that fade quickly, leaving the geometry quiet again, smooth, still. Imagine looking at a black hole from a great distance. You would see a perfectly round shadow, a sphere of darkness cut into the sky, symmetric, precise, undisturbed. Around it perhaps a dim glow from material drifting near, a soft orbiting light, reddened, stretched, gentle. Everything moves according to clear rules. No chaos, only curvature, only the deep pull of gravity sculpting paths in the simplest ways possible. Even time follows that simplicity, flowing differently depending on where you are, but always flowing smoothly, continuously, without jolts, without cracks. That is the real nature of a black hole, not destruction, but geometry, not violence, but order. And when you think about the horizon, this quiet boundary where outward possibilities end, it becomes another gentle idea. Not a wall, not a physical surface, just a place where the equations change their meaning, where the arrow of possibility tilts inward, where light loses its ability to climb uphill, where paths curve softly toward the center, and inside everything continues, not abruptly, not suddenly, but with the same smoothness that defines the outside world. A falling object doesn't feel the horizon. It doesn't sense a crossing. It simply moves along the path space-time provides. The way a leaf floats downstream, guided by the shape of the water. Every part of the motion makes sense. Every moment is governed by rules, and those rules are known, predictable, deep. This predictable calm extends even to the largest black holes. The ancient giants at the centers of galaxies, they sit quietly for billions of years, gathering mass slowly, steadily, guiding the orbits of stars, stabilizing the motion of entire galaxies, not as tyrants, not as monsters, but as silent anchors, their gravity holding structure in place. Even though everything around them is moving, stars swirling in orbits, gas drifting, dust spiraling, the black hole remains still, unmoving, invisible, steady, like the calm center of a storm that never arrives. A presence felt through gravity, not through light, a quiet core, a stillness within a dynamic universe. And when you imagine the timescale of a black hole's life, the quiet deepens even more, because these objects last far longer than stars, longer than galaxies, longer than the current age of the universe. Some will continue to exist for unimaginable durations, and only then, after those immense spans of time, will they begin their soft evaporation. Hawking radiation, the whisper of quantum fields near the horizon, particles emerging, energy carried away. So slowly you could not measure it across any human lifetime. A glow so faint, so patient, It is almost poetic. A black hole releasing its energy back into the cosmos, bit by bit, atom by atom, a quiet return, until eventually it fades, not violently but gently, as if disappearing into the same silence that once drew everything inward. And when you pull back, when you try to hold all of these ideas at once, the curvature, the simplicity, the stretching of time, the gentle disks, the smooth fall inward, the ancient giants, the boundary of knowledge, the long quantum glow, you realize black holes are not terrifying, they are serene. The most extreme objects in the universe are also the most elegant, the most mysterious, the most quietly beautiful. They take complicated matter, unstable stars, chaotic clouds of gas, and they turn them into things defined by pure geometry, pure gravity, pure simplicity. Their very existence is a meditation on the nature of the universe, on the way complexity becomes order, on the way motion becomes structure, on the way time bends and space curves and everything follows the rules, softly. And as you drift now into your own quiet space, you can let these images fade gently. The shadow of a horizon, perfectly round, a slow spiral of matter, glowing softly, time stretching like a calm tide, space-time curving, smooth as a wave, the quiet center, deep, dark, still, a place in the universe where everything comes to rest, where the equations are simple, where the geometry is calm, where even light slows its climb and slips inward. And as these thoughts float gently to the edges of awareness, you can let yourself drift inward too, not into darkness, but into rest, into stillness, into a place where your own thoughts grow quiet, where the mind softens, the body slows, and the sense of time becomes gentle. A place as calm as the deepest regions of space-time, a place where you can breathe and settle and simply be. Tonight you have wandered through the quietest mysteries of the cosmos, and now you can let them fade, let them dissolve, let them become a soft background glow, as you drift into sleep, slowly, peacefully, quietly, like light falling toward a horizon, becoming stretch, becoming softness, becoming calm, floating in the gravity of rest, and settling, at last, into stillness.